paper around, it was almost illegible. It had been faxed in. It looked like it had first been copied onto crepe paper, then crumpled up, then flattened, and then faxed in. You couldn't read the paper. I mean, you could barely make it out. The description was unintelligible to most of us. But when you're evaluating a paper to see if it contains an MD5 collision, it's very easy to come up with accept or reject. What do? You type in the two inputs and see if they collide under MD5. That's really the litmus test for such a paper. So dutifully, one of the PC members typed in M and M prime into MD5, hashed them, and out came two different digests. No collision. So that made enough sense to everybody, right? Somebody we've never heard of thinks that she's discovered some sort of collision, just clearly confused about the whole thing, and we rejected the paper. So 4 months later, Xiaoyun Wang decides to get a visa, come to the United States, to Santa Barbara, and attend the crypto conference, sit down with one of the people at the conference, and figure out why her paper was rejected. Well, it turned out that in the Chinese translation of Bruce Schneier's book, the endianness was wrong, and she had used the wrong IV. Her attack allows you to use any IV. So knowing this, she called China middle of the night, had her colleagues go right to work, fix the endianness problem, compute through the night. By the next morning, she had an actual attack on MD5, an actual collision, and it was verified by several people at the conference, and that night there was a rump session, and she announced her results. So it was quite a shock to the community that this person who we never had heard of before had just found had achieved one of the biggest results we've had in many, many years. And it turned out, when people talked to her more and more, that she'd actually been working with these functions for quite a long time and thinking about them for quite a long time. More about that in a few minutes. So here it is. Here is the first MD5 collision that's ever been found. It's a 1024-bit message M. And now I'll show you M prime. So you may not see it, but there's a little prime that just appeared by the M. So here's how M prime differs from M. It only differs in 6 spots. In fact, it only differs in 6 bits. If you look at how you should replace the existing message with the new message, you're only flipping a bit. So the 8 goes to a 0, which is a flip of the high bit. And in fact, they're all flips of the high bits. Sometimes you're turning them off, sometimes you're turning them on. 7 goes to F, that's turning it on. F goes to 7, that's turning it off. And the rest are all turning it off. Okay? So only a 6-bit Hamming distance between M and M prime. She announced this at the rump session. By the way, these two things both hash to the same value, and this value is here. She announced this at the rump session with no details as to how she figured this out. And people were, of course, clamoring for details. Add to that the fact that she spoke almost no English whatsoever. In a sense, you think it'd be frustrating, but in a sense it was exciting, because it was like this big mystery. Like, where did this come from, and how does it work, and so forth. And it took us over a year to actually figure out the crucial details, and we still don't know everything about how the technique works. This is to date still the only way we know how to find MD5 collisions. All MD5 collisions we know of, and now we have millions of them that we know of, they always vary this way. They differ in exactly these 6 bits. Nobody knows any other collisions other than these. Okay? We've gotten very good at producing them faster and faster and faster, but no other ways to produce them other than to vary these 6 bits. Okay, so what her attack does is it finds a 2-block collision. So in MD5, we have a 512-bit message chunk that we feed into the top arrow, and a 128-bit chaining value that follows along these bottom arrows. So all her attack does is it finds 2 512-bit blocks, M1 and M2, and it finds a different set of 2 blocks, M1 prime and M2 prime, and the same chaining value, and produces an output that's equal. It produces a collision. The nice thing is that the chaining value that you put in at the first part of this collision is the same, and it's arbitrary. Okay? So not only can you put in the MD5 IV, the one that I showed you a few slides back that was palindromic, you can put any value you like in there. And then the techniques, the attack, will then find you an M1, M2, 1024 bits, and an M1 prime, M2 prime, a different 1024 bits, that will collide under 2 iterations of the MD5 compression function. So in some sense, that's very nice. It's very powerful because it allows you to choose any IV. In another sense, it's not so powerful because it really just produces 2 1024-bit chunks of garbage that happen to collide. How can that be applied? We'll look at that in a little later. Okay, so it would take a long, long time to go through the attack and how it works in detail. I'll give you the main ideas, and if you have more questions, I'll list on a slide later on a place where you can find our paper, which gives a lot more details and explains step-by-step how things work. So we're going to start off looking at the internals of the MD5 compression function. And I won't look at the detailed internals because that would take, once again, a long time. But I'll give you a sketch of how it works. So here's the compression function in the lower right-hand corner. It takes in 512 bits. It breaks those into 16 chunks of 32 bits each. So the compression function works on 32-bit things. And that's because at the time Rivest designed it, that was a safe size for computers to be fast on. Now maybe 64 is a little more appropriate. The chaining value is 128 bits. We break it into 4 chunks of 32 bits. Okay? So now it's operating only on 32-bit objects. And here's the compression function. You run 64 steps of this algorithm shown on the top box. And the outputs are written as Q0 through Q63. And those are called the step values. The step values are critical to the attack. You do all kinds of weird stuff on them. In fact, this is how hash functions are built. Do lots of weird stuff on things. You put them through this phi function, where phi in the first round, and a round is first 16 steps, next 16 steps, there are 4 rounds. You put them through this phi function. The first round, the first 16 steps, is indicated on the lower box. You do this x and y, or not x and z. The next 16 steps you compute with the next function and so forth. Okay? So there are these dedicated Boolean functions, 4 of them, 1 for each round. Then, up here back in the top box again, you do this to the first of the 3 step values. You add in the 4th. Add here means addition modulo 2 to the 32. You add in w sub I, where w sub I is one of those message chunks that's scheduled according to some simple algorithm. You add in y sub I, which is just a constant that depends on the round. And these constants are the decimal expansions of sine of 1 and sine of 2. And I mean sine like the curve, from trigonometry. Anybody guess why Rivest chose to use the decimal expansion of the sine of the integers from 1 to 64 for the constants? You'll see this in a lot of designs of cryptographic primitives. They'll use the expansion of e, or pi, decimals of pi. Here we're using sine. The idea is to get something that's pseudo-random, that looks pretty arbitrary and jumbled up, but also to try to reassure people who are the suspicious type, as most paranoid cryptographers are, that he didn't carefully choose constants in order to make backdoors in the algorithm. Okay? It'd be really hard to find, a function that's natural like sine is, and engineer its decimals to behave a certain way to create a backdoor. So this is supposed to be an assurance that there are no backdoors. Those are the yi constants. The triple less than sign is, as usual, left-handed circular rotation by SI bits, where SI is once again looked up in a table, a bunch of arbitrary numbers. So we're evaluating a Boolean function, or a 32-bit logical function. We're doing additions. We're doing additions by constants. We're adding in some of the message bytes. We're shifting things around. Then we're adding in another thing, jumbling up a bunch of stuff. That produces the next step value. So from Q -4, -3, -2, -1, we get Q0. And then always using the previous 4, we get the next one, and so forth, until we achieve Q sub 63. Any questions on this? You don't have to understand this intimately to get the gist of the attack.
How can it be decimal digits? I mean, do you represent them in binary coded decimal?
Yeah.
Oh,
So
okay.
yeah.